This video presentation is brought to you by the Pro Mathematics Academy. Welcome back to another video presentation brought to you in part by the Pro Mathematics Academy. In this presentation, we'll be looking at matrices, properties, and characteristics, right? And we'll be examining these properties by also looking at questions that bring out how these properties and characteristics are particularly important. All right, so here we jump right in by looking at question number 1, which asks us to prove that if B and C are both inverses of the matrix A, then B must be equal to C. Okay, here we make a quick note to recognize that this is asking us to prove that the inverse of a matrix is unique. All right, and that's a very important property of matrices. All right, once the inverse exists, then it must be unique. So let's go. So if B is the inverse of A, then this means that A times B is equal to I. Okay, I'll call this equation number 1. And if C is the inverse of A, then it means that A times C is also equal to I, right? I'll call this equation number 2. Notice that if I take equation number 2 and I subtract equation number 1, what we end up with is AC minus AB equals I minus I. So we now recognize that we can factor out A from this expression, which now leaves us with C minus B being equal to the 0 matrix. Here we want to make a note. Okay, so when doing matrix algebra, the 0 is represented by the 0 matrix. So now this means that either A is equal to 0 or C minus B is equal to 0. And of course, this 0 is the 0 matrix. Now we know A is not equal to the 0 matrix since A inverse exists. Okay? So if A was the 0 matrix, then the inverse would not exist. But here we're speaking about the set of matrices which has inverses. Okay? So this means that we now end up with C minus B being equal to the 0 matrix as our only solution, which we can only conclude that C is equal to the 0 matrix plus B. And when we add a matrix to the 0 matrix, the result is that resulting matrix, which in this case proves, right, that the inverse is unique. Okay, moving right along. We now look at another question which gives us the transpose property, right, along with multiplication of matrices. So here we're given the following matrices, right, and we are going to answer the subsequent question. Here we're looking at part I, and it says find A transpose multiplied by B. Here we have A being this matrix and B being this matrix. Okay, so therefore the first thing you want to write down is the transpose of A. So the transpose of A, how do we write down the transpose of A? We take each row, right, and we write it as a column. So here we have 3 rows, and the first row is given by A1, 3, 4. So I'm going to write that as a column. So here I have A1, 3, 4, and I take 1, 5, 6, and I write it as a column, also 1, 0, and 2. Okay? Now we need the matrix B. So we already have the matrix B, so this means A transpose times B is actually equal to, let's copy this down, and now I multiply by the matrix B, which is minus 2, 7, 3, 1, 0, minus 1. All right, and we know that when multiplying matrices, we multiply row by column. So here we end up with the first term being minus 2 times A1, right, plus 1 times 7 plus 1 times 3. Our second term turns out to be 1 times a1 plus 1 times 0 minus 1 times 1. Here in our first column, second row, we'll have minus 6 times, well, plus 5 times 7 plus 3 times 0. Then we'll have 3 times 1 plus 5 times 0 plus 0 times negative 1. Then we have minus 2 times 4 plus 7 times 6 plus 3 times 2. And our last term will be 4 times 1 plus 6 times 0 plus negative 1 times 2. Okay? Let's bring this down a bit. So now we can simplify our result. All right, so our first term is actually minus 2a1 plus 10. Our second term is actually a1 minus 1. Here, we'll end up with 35 minus 6, which is 29. And here we end up with 3. Here we end up with minus 8 plus 42 plus 6. So that is 40. And here we have 4 minus 2, which is 2. Okay, so that's our final answer for A transpose B. Right, we move along to now write down what is B transpose A all transposed. And if you notice, I have this little reminder here, so that we can recall that B transpose times A transpose is equal to AB all transposed. Okay, so here we end up with a reverse product of the transposed. Okay, when we apply the transpose to a product, we end up with the reverse product transposed. So continuing, this will now give us A transposed times B transposed. Okay, so remember, whenever we apply the transpose to a product, it must be the reverse product transpose. Okay, so here we have B transpose A, so here we're gonna have A transpose and then B transpose, right? So this then gives us A transpose, and we know that when we transpose B and we transpose it again, we'll end up with B. So therefore, the results are actually the same. So I can write down this answer as what we had before. Right, so this question was merely testing our ability to recall this property, right, the transpose of a product, not necessarily asking us to carry out a multiplication. Okay, moving right along, we now look at question number, well, part 2 of the same question. Now it says show that D plus C is a symmetric matrix. Now let's recall the definition of a symmetric matrix, right? A matrix M is symmetric if M transpose is also equal to M, right? So for this question, we need to prove that C plus D transposed is equal to C plus D, right? If we prove this, then we have proven that D plus C is symmetric. So let's go. So D plus C is actually equal to 1, 3, 4, minus 1, plus 1, 0, minus 1, 1. And when I add these two matrices together, I end up with 2, 3, 3, 0. Okay, so now I have this matrix, and I'm now going to take the transpose of this matrix, right? Which means I'm going to take each row and I'm going to turn it into a column. Okay, so here we have 2, 3 as our first row. I'm going to write that as our first column. And we have 3, 0 as our second row. And I'm going to write 3, 0 as my second column. But I notice that it is equal to the same thing. Therefore, C plus D is symmetric. Okay, moving right along. The next question asks us to prove that D inverse times B transpose is neither an upper nor a lower triangular matrix, right? And in order to prove this, we need to recall the definition of a triangular matrix, okay? So here I have for us two definitions. The first one is an upper triangular matrix is a matrix of the form. Right now, what about this form is particularly important? Notice that below the leading diagonal, we have zeros. So all the elements below the leading diagonal should be 0. Once we have satisfied that criteria, this matrix is said to be an upper triangular matrix. So here we'll say all elements below the leading diagonal should be 0. Okay, so in order for a matrix to be upper triangular, all the elements below the leading diagonal should be 0. All right. Next, we look at the definition of a lower triangular matrix, right? And notice if we were paying close attention to what we were just examining on the upper triangular matrix, we'll notice that it is quite similar. The only difference is that we have elements above the leading diagonal now being 0. And these elements below form a triangle. So here the upper triangular matrix has a triangle above the leading diagonal inclusive of the diagonal elements, while for the lower triangular matrix, we have a triangle being formed between the diagonal and the elements below the diagonal. Okay, so let's add this note. I'm gonna copy this down, and the only thing I'm going to change here is below must be above. Okay, so all the elements below, well, in this case, all the elements above the leading diagonal should be 0. Okay, and that's how we form a lower triangular matrix. All right, one important thing to also note, right, before we jump into working this question, a matrix that is both upper and lower triangular is called a diagonal matrix. Okay, so here I'll give you an example, just like before. So here we notice that a diagonal matrix has zeros below the leading diagonal and zeros above, and that is why it is both lower and upper triangular. Okay, right? This question says D inverse times B transpose is neither upper nor lower triangular. So we need to find D inverse. That's the first step. So D is equal to 1, 0, negative 1, 1. Let's confirm that. Let's take a copy of that. So we now can write down the inverse. So we rewrote D correctly. Let's get some space here. So recall, if A is equal to submatrix A, B, C, D, then A inverse is equal to 1 over AD minus BC times DA, right, minus B minus C, okay? This is the form for the inverse. For our matrix D, the inverse is going to be 1 over 1 times 1 minus 1 times 0, well, this is actually a plus, times 1, 0, 1, and 1. So after simplifying, we should get 1 over 1 times 1, 0, 1, 1, which is the same as 1, 0, 1, 1. Nice. So now we need B transpose, and if we look back at our set of matrices here, we can write down the transpose of B, right, as minus 2, 7, 3, 1, 0, minus 1. So now taking these two results, we can now write down D inverse times B transpose, which is equal to 1, 0, 1, 1 times minus 2, 7, 3, 1, 0, minus 1. And we now multiply row by column. So our first term here is minus 2. Our second term here is 7. Third term is 3. And on our second column, we'll have, or second row, sorry, we'll have minus 2 plus 1, which is minus 1, 7, and 2. Okay, so this here represents our final answer. Right, moving right along to our last question. So here the last question says, if the trace of A is equal to the trace of D, find A1. Okay, now let's look at the definition for the trace of a matrix. Okay, so here I give you a matrix A, right, which is a M by M matrix. Of course, the matrix has to be a square matrix, right? We use the notation TR and the matrix in bracket, right? And we condense this by using our summation symbol. I equals 1 to M. Here, and in words, we say that it is the sum of the elements along the diagonal. And here, when I say diagonal, I really mean the leading diagonal. Okay? So, we can now use this property to answer our question. So let's write down the matrix for A, or let's copy it. Let's see if we can copy this. So the trace of A for this question is equal to A1 plus 5 plus 2, right? And the trace of D for this question is equal to 1 plus 1. So if the trace of A is equal to the trace of D, then this means that A1 plus 5 plus 2 is equal to 1 plus 1. So this means that A1 is equal to negative 5. Okay, and that completes this presentation. That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.